Hi, I'm Sai Shreyas Gubiarish, and in this video, I will take you through my master's research project, ACOMP, which is an adaptive cloud-native orchestration framework for distributed microservices pipeline, which is very essential in this agentic AI era. Here's the roadmap, starting from overview, motivation, the problem, objectives, and related work and sections follow on. Let's start with the basic. What exactly is this autoscaling and when it's needed? So autoscaling is an automatical adjustment of compute resources in response to workload demand without any need of human intervention.
Now, let me explain you through an example of Amazon web application where the users will be able to see the front-end service, and when a user clicks on product, he'll be able to see the product page, and when he tries to buy the product, he'll be able to see the cart services, which is usually managed by the servers, and each servers being attached to the service. When number of users increase on each service, there is auto-scaling decision taker who manages and increases these services continue smoothly. This is how auto-scaling plays a key role in managing the service.
So, like this, autoscaling exists across every major platform. On AWS, it's of EC2 autoscaling group scale, mainly based on CPU or memory load, and EKS has its own horizontal pod autoscaler, HPA, which scales pod replicas once a metric crosses a threshold, and is of just increasing pod size. And Azure AKS and native Kubernetes often similar tools like VPA for vertical resizing and replication, Kera for event-driven scaling from queues, and all these fail to autoscale, as I mentioned in the current agentic workload scenarios. So, how did I get the idea of ACOMP? It came from two reasons mainly. Academically, when research papers like Zarai, who reviewed over 60 autoscaling papers and found no operational explainability, and Zeus taxonomy found pipeline level coordination isn't even a category. And dependency aware approaches, when they exist, can cut costs and latency. And then industrially, unmanaged scaling cascades elevate latency during spikes, and HPA VPA conflicts cause thrashing and wasted compute. So the gap was very clear, a need for a layer that's pipeline aware, conflict resolving, and auditable all at once. These gaps translate into three concrete problems in autoscaling today. Let's have a look at those three gaps. The service scales in isolation is the first one. When front-end spikes, nothing wants the services behind it or dependent on it. Only that service gets scaled and causing problems to other services. So the latency increases. And HPA VPA conflict enable together the issue contradicting actions, causing pod thrashing, and there is no explainability. And even reinforcement learning and current existing machine learning controllers make decisions where engineers can't audit or reproduce and can correct the scaling issues within their organization. The research objective actually addresses these gaps. 4 objectives: designing a pipeline level coordination layer above HPA and VPA that propagates scaling pressure using calibrated work factors, resolve horizontal and vertical conflicts through a deterministic priority-based policy engine, produce structured per-cycle decision logs, no machine learning expertise or models required, and evaluate against 4 comparators across 3 scenarios, which we'll be seeing in upcoming sections. I have reviewed 15 papers and put across 4 of these clusters. Firstly, reactive threshold scaling like Smart HPA only works per service, sadly, and machine learning approaches are powerful but hard to interpret and audit. Dependency-aware orchestration gets the best latency but often only in simulation, or it might require ESTO mesh or have certain dependencies. And systematic reviews confirm it. Explainability is absent as an evaluation dimension, and pipeline level coordination isn't even recognized. Moving on, so here's what I built to close those gaps. ACOMP runs a 15-second deterministic control cycle with 5 components which can be configured as per the organization's requirement and scaling dependencies. The context map holds the dependency graph and work factors. The collector polls Prometheus in parallel per service, not sequential. This is what differentiates from rest of the others, making the scaling decisions even more better. The policy engine is the brain of the ACOMP and classifies the pipeline states and computes decisions. The Actuator patches deployments in upstream first order, and decision logger writes 1 JSON line audit per record per every cycle. Nothing here needs machine learning and all are deterministic by design. So what's new? These are the features I'm introducing with ACOMP where rest of the papers or currently existing systems doesn't have. A live explainability API on port for the developers that answers why scaling was done and per service cooldown. So one pressure service can scale without disturbing the stable ones. 3 operating modes: strategic, aggressive, and conservative depending on the needs, which are switchable live and event hour pre-scaling for planned traffic like Black Friday or such events. Parallel polling that cuts detection latency from 3 seconds to 0.3 seconds. And slope-based pre-scaling that lowers the CPU threshold before a spike even lands. Now let's look at how ACOMP's policy engine actually classifies these pipeline states. There are 4 pipeline states. Healthy means no action needed. Upstream load pressure means scale and propagate downstream. Downstream degradation suppresses the scaling and alerts instead of making those worse. And pipeline ceiling clamps, scaling and alerts when limits are reached. This state machine is what keeps ACOMP from every making blind decision or uncoordinated decision. Now, this is the core idea evaluated on online boutique web app, just like the one I showed on Amazon web app. When front end scales one by one, how much should each downstream services scale? No one knows. The answer actually comes from the observed request rate ratios under real load, not a trained model. When a front end is scaled twice, then the card services, which has a dependency of 2, gets multiplied by the dependency factor, wherein twice getting multiplied by a factor of 2, eventually making it scaled 4 times. Whereas product catalog scales to 6 times. And checkout, as you can see, you might ask 1.5, what does it mean? So it means scaling one pod and then half a pod ready to scale whenever needed. Even a small spike in that pod can make it the whole pipeline aware. These live in a plain config file editable by any operator as required and when.
Now, let's look at how ACOMP works on this Amazon web application that we went through earlier. Let's have a dependency factor of front end as 1, wherein all the services are dependent on front end, as I have stated here. And let the product services as dependency factor of 2 and card service as a dependency factor of 3. Unlike all other autoscalers, our ACOMP has this dependency factors and scales the pods accordingly. So when front end scales by a factor of 1, the rest of the services who are pipeline aware and dependent also get scaled eventually, and doesn't stop users from getting blocked of using the Amazon services of all the dependent services. In this way, the whole pipeline is being scaled and dependency aware, and this is how ACOMP has certain features as I explained and works.
Now let's look at the methodology. So the methodology has 5 stages, mainly designing the architecture from literature review, build and unit test these 5 modules as Kubernetes control loop, configure 4 baseline comparators, run against all the 3 scenarios under identical cluster conditions for every comparator, then analyze the results against my research sub-questions. Let's look at the 3 scenarios I evaluated ACOMP against. Firstly, scenario 1 rams 10 to 200 users over 50 seconds and answers how does ACOMP pre-scale downstream before the threshold even breaches. Scenario 2 holds the users for 30 minutes and checks whether ACOMP stays stable and SLO compliant under sustained pressure and not taking any irrelevant scaling decisions. Scenario 3, second latency fault into the recommendation service randomly and checks if ACOMP correctly suppresses the scaling instead of scaling the wrong services like other baselines do. Let's look at the baseline comparators I use for this research. There are 4 baselines: Smart HPA from Ahmad, where it cuts the over-provisioning but still has no pipeline awareness. PBScaler uses a trained classifier but needs HTO and produces no audit log. And I'm using these 2 papers, GitHub code bases, to compare against ACOMP, and also the native HPA is simple but purely reactive per service. Native VPA right sizes pod but doesn't coordinate with horizontal scaling at all. So the evaluation metrics, it's around 4, where firstly P99 end-to-end latency, which considers worst case use visible response time, not the best case. SLO violation rate notes percentage of requests breaching the 500 millisecond threshold. Scaling oscillation index considers total scale events per hour, lower is more stable. And recovery time to SLO on how long it takes to return below threshold after a spike or fault, and have referenced the papers I took these metrics from. Now let's look at the results I achieved through ACOMP. Firstly, scenario 1, under Bursty load, held P99 latency 79 milliseconds with just 1.6% SLO violation and about 180 audit logs produced of why the decision of scaling was taken. Comparing that to of Smart HPA at 1193 milliseconds and PBScaler of 1622 milliseconds, and rest averaging like SLO of 3.99%, and scaling events were around average of 33. ACOMP only took 15 scale and the system was very stable, and the other SOI and RTTS following. For the scenarios 2, this is the headline results where ACOMP achieved around 369 milliseconds and only 1 SLO below 500 milliseconds, making it as a 2%, and the rest averages as below, where RTTS was around 64.56 requests per second, but ACOMP was very less than what they all average, and SOI of 54.38 seconds, but wherein ACOMP only took 30 events per hour. For the scenario 3, when I injected a fault into recommendation service, ACOMP posted the lowest P99 of 265 milliseconds, where others average 927 milliseconds, and SLO as well, only around 2.68%, others around 5.24%, and about 193 audit logs per record for this scenario, because it correctly suppressed scaling instead of reacting to the wrong service, and others averaging for P99 around, as I mentioned, 927. So the implementation, I'll take you through on the Azure portal. This is the Azure portal where the ACOMP was implemented, and I have created a cluster under Kubernetes service AKS for ACOMP, assigning certain nodes and configurations that were needed. And it also has Azure Monitor, where each insights of ACOMP nodes that were created, where you can see total 3 nodes I'm using and how many times it fails, or the usage metrics as accordingly, which even though we are not using as a metric for ACOMP. So in my configuration manual, I have exactly shown how to replicate my ACOMP solution, mentioning the prerequisites, Azure cluster creation, connecting the Kubectl nodes, and I'll show you directly here through the Cloud Shell session. You can see I'm getting the credentials and setting the resource group name, and I'm cloning the ACOMP's code base from GitHub directly. So I have implemented ACOMP on the Azure portal by creating a cluster on the Kubernetes service or AKS from Azure, and setting up the relevant nodes and Kubernetes version required for this research. As you can see, we can use the inbuilt Azure monitors for logging, and currently I'm using 3 nodes for this experimental purpose, and how the nodes memory or CPU was used, even though I haven't used such metrics for ACOMP. On the other end, you can see the direct monitoring of the node pool performance, the pool network, the memory, how it was managed on Azure. So moving on, we'll see how we can actually implement Azure on this cluster, where I have clearly mentioned in my configuration manual of what the prerequisites are and how to create the cluster. Now let's see how the Kubectl works. So as you can see, I'm pulling my GitHub code base for comp and then setting it up, and the nodes are now in the ready state to be deployed. And the Google online boutique that I mentioned is as accordingly, as you can see the cart and the other services of how this can work. So this is where I'm using locust for load purpose and injecting more users, and you can see all the 11 services of Google boutique are running. Now let's run the scenario 1 Bursty load. As you can see, it starts the Bursty load capture starts replicating, and all 3 baselines are compared against this, and all the 4 of it are being done, and the results are directly being displayed over here. And even the plots of figure can be seen on my GitHub by the help of the plot scripts that I have for each scenario, where each scenario runs and the metrics is directly plotted as an image. And the Actuator pie, where the decision is taken, and the policy engine, the brain of the ACOMP, is also within the code base, and users can directly replicate it. So in this way, I run different 3 scenarios and capture the logs of for ACOMP, and directly comparing it against the GitHub code bases of PBScaler and Smart HPA, as you can see, and the rest within the Kubernetes of AKS autoscaling of VPA and HPA, all according to my config file, and the results captured accordingly. Moving on to the discussion now. Now, let's discuss what actually makes ACOMP different and makes it more essential. On dependency propagation, scenario 2 is definitive, answering the question. Alone stayed under SLO because work factors pre every dependent service. The instant upstream pressure appeared while baselines waited for the breach threshold individually, making it more latency creation. Creating a cascade. On performance, ACOMP won the best across all the metrics that was captured, and on explainability as well. 528 structured audit records versus 0 over all other baselines compared. Now the major factor, what's the real world impact of it? Fears the cascading incidents and on-call pages, lower cloud spend through right-side scaling, faster incident review from those audit records, and no ML expertise or models needed, and easily integratable with above existing solutions as a coordination layer, not as a replacement. So to conclude, let's look at ACOMP's research has achieved and created an impact. Mainly, the pipeline level coordination, deterministic, and auditability is what closes the gap. 15 reviewed papers left open, and the current existing systems leave open. Work factors propagate scaling across dependencies simultaneously. 528 structured records versus 0, as I mentioned, and the lowest P99 or other metrics compared in all 3 scenarios. It's production ready for the features like 3 modes, event profiles, live explainability. All this makes ACOMP very essential to the current cloud infrastructure system to make autoscaling better. Thank you.